So what we're getting into today, and we're going to talk about this on Friday, and probably just a little bit of recap and review next Friday as we move through. Again, remember next week's kind of a wonky week for us, with no classes on Monday due to the eclipse, and then an exam on Wednesday. So we're going to cover the majority of chapter 14 here over these next 2 days. But we're going to use next Friday as kind of a recap and review day, just to kind of catch up any loose ends, and if there's stuff that we didn't talk about in a whole lot of detail, give us a chance to kind of reacquaint ourselves with acids and bases before we finish out the semester with gases at the end here. So we need to start out our discussion of acids and bases by describing really what they are. And the reason we kind of pull out acids and bases as different from solutions is because they do have slightly different properties than your average solution. Whereas most solutions involving ionic compounds have some level of saltiness to them, or just a general kind of ionic sensation, acids and bases do have properties associated with them that are different. So, for example, acids in general have a sour kind of taste. Now, I see some of you have found the last bullet point here on the slide that says don't taste your chemicals. And obviously in a laboratory situation, that is definitively true. However, we do have some context for acids and bases in normal materials. So, for example, acids we can find in certain kinds of citrus fruits, lemons, limes. That sour kind of feeling they have comes from the acids that are in them, citric acid in particular. Vinegar is sour because of the acetic acid that makes up that particular solution. Bases, on the other hand, have usually a slippery kind of feel to them, and a bitter taste. Where might you encounter those? Well, most common would be something like baking soda. Baking soda is a sodium bicarbonate solid, and if you taste that, it's going to have a bitter kind of flavor to it because of its basic nature. Antacids also have similar kinds of that kind of chalky, bitter flavor that most antacid companies try to cover up with fruit flavors or mint flavors. That's the active ingredient. That's the base in them coming through. Slippery nature. We can think of things like soaps. That soap-like effect is not is common to bases. You might find it in things like drain openers, like Liquid Plumber or Drano, have sodium hydroxide and bleach in them usually, and both of those components are basic, and that's actually how they break down the organic components in your sink, like hair and grease, without corroding the pipes themselves. Both of these substances will change the colors of certain kinds of dyes. We call those dyes indicators. We use them to indicate changes in pH. More on the pH scale on Friday. Many acids are very reactive towards certain types of metals and will cause those metals to corrode in small ways or in large ways. And acids and bases, generally, when we combine them, neutralization reactions take over. And that usually results in the end product being water and some kind of salt as a result of those neutralization reactions. Now, we've seen these kinds of reactions in different ways and forms before. We just maybe not necessarily call them acid-base reactions at the time, or acid reactions in the case of acids with metals. We called them single replacement reactions or double replacement reactions, reactions that form water, reactions that form gases. These are all reactions involving acids and bases for the large part. We just called them something different when we covered them originally, which is also why we're not going to spend a whole lot of time talking about acid-base reactions other than just in the context of what we need to know and how they fit into kind of this overall picture that we are painting of acids and bases overall. When we discuss acids and bases, one of the important properties of those acids and bases are related to something called strength. Now, the difference between a strong acid and a weak acid has everything to do with something called ionization. Ionization is just the property associated with how well does that acid or base split into ions. Now, believe it or not, we've covered this particular concept before as well. When we talked about solutions for the first time, we talked about the idea of electrolytes, substances that conduct electricity. And if you recall, the ability of a substance to conduct electricity had everything to do with the number of ions that were present in that solution at any given amount of time. The more ions that are present, the stronger that solution was able to conduct electricity. Well, this is true also for acid and base solutions as well. We can use ionization, we can use electrolyte capability as a measuring stick for how strong or not strong a particular acid or base is. So one thing that we have to recognize about acids and bases is that when we consider them to be strong, we would consider their ionization to be complete, 100%. And that shows out in a chemical reaction as a one-way reaction. So if I look at a strong acid like hydrochloric acid in water, I'm going to see it ionize completely into hydrogen ion and chloride ions as part of its reaction in forming a solution. Same thing with a strong base. Strong base is going to split up completely into its ions. Weak acids and bases, on the other hand, we don't see that complete ionization taking place. What we see instead is partial ionization, incomplete ionization. In terms of electrolysis, what does that mean? That means we get weak electrolytes. We get substances that can conduct electricity, but they do so very weakly and have low conductivities by comparison to strong acids and other strong electrolytes. From an equation standpoint, we show these reactions in terms of reversibility. So this side was all of our strong action. On the weak side, we might have something like this, where acetic acid will partially break down into ions. And ammonium hydroxide, which is another weak base, will partially break down into ions as well. But the key in this is the reversibility. The fact that that arrow swings both directions means that there is a constant changeover from the ion side to the molecular side, and from the molecular side to the ion side. In fact, we can look at these more closely, and what we're going to find is that, roughly speaking, the majority of the time, these reacting species end up staying on the molecular side. Depending upon the strength of the acid or the strength of the base and its concentration, those values can swing wildly from anywhere between 10% ionization to less than 1% ionization. Which means that the majority of the time, even in the stronger cases, 90% of those molecules stay molecules and don't form ions in the process. So, unfortunately for us, there is no real hard and fast way to remember which acids are strong and which ones are not. This is your list of strong acids. Now, you'll notice on this list, there are some familiar names, things that you've seen before. Things like hydrochloric acid, things like nitric acid, things like sulfuric acid. Those acids are common strong acids, and they find their way into a lot of different kinds of products. Hydrochloric acid is found in certain types of toilet bowl cleaners. Nitric acid is a precursor in the production of nitrogen-based fertilizers. Sulfuric acid is found in a number of different kinds of compounds. You might see it known by its trade name, which is, I believe that one is muriatic acid. That's hydrochloric. Okay. Escaping me right now. But it does have common way. There are common uses for it as well. On the strong base side, these ones are a little bit more predictable. With the strong bases, we tend to focus mostly on hydroxide compounds found in group 1 or in group 2 of the periodic table. So if you're looking at a hydroxide compound in group 1, we know it's a strong base. If we're looking at a hydroxide compound out of group 2, we know it's a strong base. Now, one important little kind of piece of information here. The compounds in group 2 are not terribly soluble in water. So there is that aspect that we have to worry about and deal with, is from a solubility standpoint, they don't tend to dissolve particularly well. But those parts that do dissolve do completely break apart. And that's why they get classified as strong bases, even though their solids are not the most soluble things in the world. So again, the key here, the thing that you want to write down for the strong bases would be your group 1 and group 2 hydroxides. So unlike the strong acids where, you know, it's more of a list and we just kind of have to know what's on the list and what's not on the list, the periodic table gives us a lot of information here as far as the strong bases are concerned. Now, the thing to know, if you're looking at strong acids and strong bases, if you encounter an acid or a base that's not on one of these two lists, you are safe to assume that it is a weak acid or a weak base. The question becomes, here are some common examples of each of those. How do I go about identifying a compound as acidic or basic just based on what its chemical formula is? Because if you look at the lists here, a little bit of variation, a little bit of variability. How do I know that I'm dealing with an acid, or if I'm dealing with a base, or if I'm dealing with something else entirely? To answer that question, we need to be a little bit more fine about how we actually define these acids and bases. Now, for the most part, thus far in the course, we've taught you to look for hydrogens and hydroxides when identifying acids and bases. Compounds with hydrogen in the front are acids. Compounds with hydroxide on the back are bases. That definition is something known as the Arrhenius model. The Arrhenius model is largely based on the behavior of a compound in water, and falls into basically two categories. Compounds that form hydrogen ions in water are acids, and that's why we put the hydrogen in the front of the formula. Compounds that produce hydroxides in water are bases, and that's why we put that hydroxide, that OH, at the end of the formula. And for a considerable period of time, this definition actually works really, really well. I can easily identify from a chemical formula what an acid is and what a base is and what they are not. What we run into with this particular model, however, is that there are a couple of problems. One of the problems is based on a fundamental assumption that we made. The other is based on the fact that this particular definition is too exclusive. There are too many things that are being left out by this model that we know exhibit acid or base behavior. So let's talk about the first problem. The first problem in the Arrhenius model is that H plus that we're talking about that forms in water, it doesn't exist. if I go to the molecular level for water and I throw in an acid and I continue to look at the molecular model of that water with the acid in it now, the thing I'm not going to find are H plus ions. What happens to those H plus ions from the acid is that they start to attach themselves to the water molecules inside of the solution. And so what we get instead is not H plus ions, but rather hydronium ions. Hydronium being H3O plus. So that HCl that we were talking about, when we put it into water, was actually making hydronium ion and chloride ion when it dissolved, not H plus. It seems like a ticky-tack little thing to kind of worry ourselves with, but it becomes kind of an important point when we start trying to look for other ways of defining acids and bases. Because if the very thing that the model describes as being this is what makes an acid isn't actually true, then we need to rethink of that definition of an acid. So this problem, along with that problem of exclusivity, brought about a change in the way that we define acids and bases. And so while the Arrhenius model is good at when we're kind of first starting, trying to identify acids and bases based on their formula, we need a better model when we start getting beyond just those simple examples. And that better model is something called the Bronsted-Lowry model. In the Bronsted-Lowry model, what we focus on instead of formula is reaction. So we think about acids and bases as being things that react with each other. And we base our definition of the acid and we base our definition of the base based upon how they react and what they do in that reaction. Now, the beauty of this model is in its simplicity. All I need to do is track the movement of the hydrogen ion. The thing that loses the hydrogen ion, that's my acid. The thing that absorbs or accepts that hydrogen ion, that's my base. So if I can learn to look for how is the hydrogen ion moving, I can begin to understand where my acid is and where my base is. So under the Bronsted-Lowry definition, both of these reactions are acid-base reactions because they both involve the movement of a hydrogen ion. The difference is twofold. Which direction is the hydrogen ion moving? In the first example, we see that the hydrogen ion is moving to the water. And that allows us to define HCl as an acid. In the second example, we see that the water is moving the hydrogen ion to the ammonia. And that allows us to generate that ammonia is in fact a base. Under this definition, we're allowed to talk about ammonia as a base. In the Arrhenius definition, we weren't allowed to do that because there's no hydroxide for ammonia to drop off in the water along the way. But now we can see how it goes about. Why does that hydroxide show up in ammonia solutions? It doesn't come from the ammonia itself. It comes from the water as the water transforms. Under this definition, every acid-base reaction appears the same. It all involves the movement of the proton, the hydrogen ion, from the acid to the base. And so this is the model of the atom, or excuse me, the model of acid base that we're going to focus on primarily the rest of the way here. Because it has so much utility to it. So for these next couple of slides, don't worry about copying down every detail. The slides are in Blackboard. What I want you to do is just look at how we can expand our definition, in particular of bases here, and of acid-base reactions under this model. So again, carbonate has no hydroxides. We wouldn't identify it as a base under our old definition. But when we see how carbonate ions interact with water, we see that, oh, wait, they accept a proton from the water and they generate that hydroxide. They're basic. This reaction between hydrofluoric acid and carbonate ions, where we can see that the hydrofluoric acid is giving its proton away to the carbonate, that's an acid-base reaction. And now we have a definitive way of showing its acid-base nature. Now, one common thread that kind of wove its way through all of this was this concept here about, we saw this in water. In some cases, water was accepting protons. So as water turned into hydronium ion, it was acting as a base. It was taking that extra proton and becoming hydronium. As we saw in the previous case, here we have water acting as an acid. Water's giving its proton to the carbonate and creating hydroxides in the process. This dualistic nature of water, where it can act as an acid in some circumstances and as a base in another, that's a phenomenon known as amphoterism. We can call those substances that exhibit this dualistic property amphoteric. Water is the most common example of this, where because of its unique position on the pH scale being right in the middle, and because of the fact that it not only can give away hydrogens, but also take them in, it puts it in the position of acting as acid in some situations and base in others. But it's not the only one that does this. Bicarbonate is another prime example. Bicarbonate ions usually act basic. But if you put them in the presence of a strong enough base, they'll actually act acidic. And yield different kinds of results as a consequence. So if I do a titration with a bicarbonate ion, I can do it with acid and I end up getting carbonic acid, carbon dioxide, and water. Or if I titrate with base, I can end up getting carbonate ion and water molecules as a result. One last thing, and then we'll revisit this on Friday as well. Something that you might have noticed is that there is kind of a relationship between the reactants and products. I can pinpoint individual products and show that they are one hydrogen away from the reactant that they started with. This is something known as a conjugate pair. Conjugate pairs come as a result of these acid-base reactions, where they'll act as a acid on one side and as a base on the other side, based upon their ability to gain or lose that proton. So we'll talk more about that. That's where we'll start on Friday.